Hey everyone, good afternoon. I know this is like the last session of the afternoon. I hope you've all had your coffee. We'll get through this together. Like you said, my name is Jonathan Austin. I'm a project manager with GPI Geospatial. We're a full-service mapping firm on the East Coast of the United States, specializing in remote sensing, so LiDAR, photogrammetry, all that kind of good stuff. So today I'm going to talk about how we can use remote sensing technology to build asset inventories. So when you're building your GIS database and you need to know what you have, what you own, what's out there, the condition it's in, this is how we can use that technology to solve that problem. I'm also going to talk a little bit more about the future, where things are going in terms of automation and AI. So I'll get to that as we go along. Forgive my outline here. It seems like the PowerPoint gods were messing with me on it, but this is kind of the outline. We're going to talk about 3 different types of projects that I've worked on using remote sensing, kind of case studies of different ways that we're using mostly mobile LiDAR, but also UAS, photogrammetry, aerial LiDAR, and such. And then we'll get into automation. So when we're talking about remote sensing technology, got a little definition here from USGS about what remote sensing is. But these are kind of some of the things that we're talking about with remote sensing. Radar, I know in GIS, this synthetic aperture radar that's available now it's radar from satellites, basically. This kind of cool new thing. Or ground penetrating radar to see below the surface. LiDAR, sonar, photography, and even pavement profiling. I'm also going to talk a little bit about accuracies. We like to talk about how accurate your data is. I will say I'm not a land surveyor. I'm not making any claims about your data and how accurate it is. Just based on what I've seen with the projects I've worked on in remote sensing. So we're talking about absolute accuracy, which is where am I on the planet? And then how far is this from that? So when you're taking a measurement, how accurate is that measurement in the data? Now, when do these accuracies matter? I've got a couple examples. On the left here is using LiDAR to calculate bridge clearances. So that's when relative accuracy would really come into play. You want to know precisely how high that beam is off the roadway so a truck doesn't hit it. So that's where you want really good relative accuracy of the data. And then on the right side, that's a design survey. So if you're going to have an engineer out building a new bridge or a highway, they need to know pretty precisely where that road is going. It's going to have to tie into other features around it, make sure that they're demolishing the right houses, along the way, that kind of thing. So that's where our absolute accuracy will come into play. Now, when we're talking about remote sensing, a lot of times we like to talk about the cool toys. So these are just some of the examples of the cool toys that I've gotten to play with in my career. We have, fixed wing aircraft, rotary wing aircraft, hydrographic survey. We got a LiDAR scanner on a boat there, drones, static scanning. I don't have a picture of it yet, but if you saw Jamie Gray's presentation about SLAM technology earlier, it's a cool new toy with collecting LiDAR. Instead of using survey control or GPS, it just uses features around you to determine where you are. And just a quick plug for Jamie, if you come to the social later, he's going to be showing off some of that technology. So stop by the GPI booth and you can see that. But the main thing is, what tool we use is determined by the project. So what are we trying to measure? What are we trying to achieve with the project? That's how we're going to determine which platform we use, which type of sensor, that kind of thing. So this is one of the projects I'm going to talk about. The Maine Department of Transportation, every year, if you've ever been to Maine, it gets very cold, and it takes a toll on the roads. So the freeze-thaw cycle really destroys their asphalt. So repaving is a big deal for them up there. And we've worked with them collecting mobile LiDAR data on their roadways. They kind of pick the worst roads each year. We go out and scan it and then use that LiDAR data to create a really nice model of the roadway. So here's an example of what that roadway looks like. And in this case, they're taking a cross-section of the pavement from the mobile LiDAR data every 5 feet. So they want that really good relative accuracy. So they can see every divot in the pavement. They know, if it's settling, where the potholes are, so that they can figure out which roads to prioritize for repaving. This is another one, a little bit closer to home, South Carolina DOT, doing a similar thing. In this case, it's for cross slope analysis. So you can scan with mobile LiDAR, then map the pavement itself, and then determine, where your cross slopes are falling within tolerance. Here's another example. This is the New Jersey Department of Transportation. Wants to update their straight line diagrams for their roadways. So what they're trying to figure out is where along a roadway, if you can kind of see that picture there, where an intersection falls, where there's a stopped light, and they draw it out on a straight line, which makes it easier to read. And we're working with them using mobile LiDAR and imagery and collecting all that data, then updating the straight line diagrams from that. Another part of this project, just like Google Street View with the 360 camera, we've got one of those. It's a Ladybug 360 camera mounted on the vehicle. And they're actually using that imagery and photogrammetric, like stereo mapping abilities to map from that imagery. So we're collecting a picture every 5 meters along the roadway. So they're getting a lot of detail. And then that imagery is being used to update their statewide video log of all their roadways. And then another example I'm going to be talking about as we go through the steps of kind of this using remote sensing for this purpose is sign and pavement inventory. This is the city of Salisbury in Maryland. So they wanted mobile LiDAR and imagery for every street in the city limits. And then the imagery was going to be used to conduct a pavement analysis, and then the LiDAR and imagery used to do a sign inventory. So I'll go through all the steps of kind of how we plan these missions and then getting to the deliverables. So mission planning, it's really specific to the job. We like to see the exact limits, what we're trying to gather. If it's just within a roadway, then okay, mobile LiDAR is going to do it. If we want a wide area, then maybe it's going to be an aerial platform. Or, if it's out in a swamp, maybe we need surveyors out there, that kind of thing. For mobile LiDAR, this is an example of that planning. We're going to scan both directions. We're going to scan multiple lanes and try to get redundant data. As you drive, you can drive highway speed with this, and then you're going to have some holes where other cars are going by. So we'll drive every lane to make sure we're filling in all those gaps. And up top is an example of how we might plan an uncontrolled mobile LiDAR survey. So where we don't necessarily need the high absolute accuracy, we just need to see what's out there. Then we won't use any survey control. We'll just drive and make sure we collect LiDAR in all the limits. And then the bottom picture is showing how we might lay out targets for a mobile LiDAR project. To make sure we're getting really good accuracy, even on where just the relative accuracy is what's important, we want to make sure that our data is good, that it's on state plane coordinates. So we use base stations, and we'll plan out usually with either primary control that's provided by the client, or that a surveyor has gone out there and provided for us, or in this case, this is using an NGS benchmark. We set up a GPS unit while we're out collecting. We could also use a CORS station, continuously operating reference station. And this is true for any kind of trajectory-based LiDAR collection. So anytime you're in motion. This is just an example of a tripod set up on a benchmark. Typically, we'll set up our own GPS units and then use the CORS as a backup. Here's an example of mission planning for an aerial project. So kind of similar to mobile in that we want to see the limits. and then we're planning it based on that, setting up the control points, which are those hexagons on that picture, and then determining what altitude we're flying based on the desired GSD, which is our ground sample distance, essentially the resolution of the final imagery. And then how far we want the LiDAR to go out, the swath of it, the density of the LiDAR is all going to come into play. So another option for mobile collection is video. So this is just a little example of how video can be used for collecting assets along the roadway. So this tool here is showing the video being collected. That's not really working. And then along with the GPS coordinates. So we can actually use this video, since we know where this video was captured, to find out rough coordinates of this asset. And then here's an example of the 360 imagery I mentioned earlier with the Ladybug camera. So that's using 6 individual cameras for a total of 30 megapixels. And then, it's very similar to Google Street View. So here's an example of what that might look like. So when we're capturing a picture every 5 meters, then you've got all these points along the roadway that's based on the mobile trajectory. So that's the GPS unit with the mobile LiDAR unit. And we can then use this map up here to make sure that we covered everything. We got imagery on all the limits that we need to, and that we can then move on to processing. I mentioned using the imagery to collect features. This is an example from the New Jersey project. So it's actually taking 2 pictures taken in 2 different points and then using that to triangulate the road width here. So in this example, they're measuring the lane width, and then that's going to go into the database. That imagery can also be calibrated with the LiDAR data. So they're captured at the same time. They're both geo-referenced. This is an example of what we can do with that calibrated imagery is then colorize that point cloud. So you've got RGB values associated with each point within the point cloud. Makes it a little easier to identify the features. Typically, when you're looking at LiDAR data, a lot of times it's just going to be the reflective value of that LiDAR data, which you can see features, but a lot of times, we're human beings. We want to see it as we would see it in the real world, and that's where the imagery helps. For the actual attribution of features, so we've gone out, we've scanned everything. Now we need to locate features to build our database and attribute them. So this is an example of using the LiDAR data to attribute a sign feature. So you can see there's a whole list of attributes, including the coordinates, the clearance of the sign off the ground. We're looking at the imagery and determining the condition of it, good, fair, poor. The sign itself, the panel, and then the support. And then all of that can be used to update a database. So this is an example from that Salisbury, Maryland project. I think initially we estimated about 10,000 signs, and we ended up collecting almost 12,000. And that was all done in the office. So it was, about 3 weeks of data collection out in the field. And then, when the weather's nice, and then that data can go in the office. And then, it's kind of what I compare this to. Typically, this is work you might use an army of interns to do. Send out your interns with a GPS unit. What this allows us to do is have those interns in the office, keep them out of danger, keep them out of the weather, and collect the features that way. So next topic is the automation. So this is kind of where it's going. We're collecting all this data. We're having our interns collect all the features in the office. And it's still a manual process. So where this is going in the future is training AI models to find these features, locate them, even attribute them to some degree. So this is kind of showing the workflow of machine learning, where you're taking your imagery, you're putting it into the AI, getting your results, you QA, QC it, you fix the errors. The computer is always going to make errors. So this is where the human being is still going to be a vital portion. Computers are really good at repetitive tasks and calculations. What human beings are good at is interpreting that data in a way that's valuable to a human being. So that's where the human being comes in. You can feed that data back into your AI model and train it so it's even better the next time. So this is an example of taking video and then running it through an AI framework to detect sign features. So you kind of see as it's going, it's going to find a sign and highlight it that's saying, hey, I know there's a sign here. And if we know the position of this video, then we can use our triangulation to determine where that sign is located. You'll notice most of them are showing up red, where it's trained just to find a sign. So that just means, hey, there's a sign here. It doesn't really know which one. I think at the end here, it'll detect the stop sign and actually know that it's a stop sign. There you go. You can see it's actually white, showing that, okay, yeah, here's a stop sign. And this is just giving the AI lots of training data. So you have to keep feeding it new data so that it can learn and be able to do this kind of detection. So one thing that, this is another way we're going forward with AI is using deep learning. There's tools in ArcGIS to be able to do this. We're using, I'm kind of lucky where I'm at. We have a lot of data. And so we're using that now to train these AI models and get them more and more precise. In this case, it's taking an aerial orthomosaic photo and then determining where there are manholes in that picture. So you kind of see little circles. That's where the AI has gone through and found a manhole for each one of those. This imagery was, I think, 3-inch resolution. So a manhole is a pretty fine feature, so we want really fine resolution to be able to detect it. And then there's also always a possibility of false positives. So anything circular that kind of looks like a manhole, the computer is going to think is a manhole. And it requires going through, QCing it, removing those false positives, and then retraining that model. So here's just another example. Once those polygons around each manhole are found, you convert them to point features, which can be used to build the database. And there are pre-trained models available online. I found you have to then train those on your own data to really make them work well. So we're kind of just working on making our own based on the imagery that we have. And I have some lovely stats on just couple of the examples that I've worked on. Just after one iteration of training the model. So the bar on the left side of these graphs is showing what's the baseline. So those are actual features in the imagery. And then on the right side is different accuracy levels of how many features the AI detected. So I'm finding we're getting more of the features as I train the model more. Also, strangely enough, though, I'm finding more false positives. So I think just through training and being able to filter out that data, you can really get a good model going. This is just some more statistics about what I've been seeing between the two iterations. And then this is just another example of using the data, training it to find, say, paint stripes, linear features. What this is doing is, this is a very repetitive task for a human being to go through and map all these features. So the AI is going to help alleviate that task, let your experienced mapper do more technical QC type work. And then just kind of where things are going, this is just an example of how this is a self-driving vehicle, a sample of how it sees the world. So this is kind of real-time identification of features while it's driving. So it's using the same remote sensing technology we are, maybe not to the precision or accuracy, but then using that imagery to detect features. Finally, this is my own little remote sensing bot here, cleaning my apartment. So it's got a LiDAR scanner in it, scanning my apartment, probably sending it to the Chinese government, but that's fine, they can have it. So yeah, building a map with remote sensing of my apartment. With that, that's all I got. So I can take questions. Any questions? Oh, yes? For the aerial imagery? Yeah, so I believe it's looking for objects. So it's trying to detect objects in the imagery. So you can choose what it's looking for. I let it look for whatever it can find in that imagery. So any attributes that raster contains, it's going to look at to determine the features. But yeah, if you want to, you can set it to only look at colors, only look at shapes, reflected values, whatever. It depends on your data, really. Yep. Do you have Yeah, so we drive with traffic, so highway speeds. We found that you start to lose a little bit of the value of the density if you're going, some places allow you to drive 70 miles an hour. And when you get to that speed, we see a little diminishing in the density of the data, but you can make up for that by driving multiple lanes. But yeah, we drive with traffic, so it minimizes the need for maintenance of traffic, closing lanes, anything like that. Yes? Yeah, so I'm not entirely sure of the licensing, like how that would affect using that free data. It's certainly possible. What we like to collect new data just so we know we have the most up-to-date information about that site. We can also control the accuracy of the data better that way when we're collecting it ourselves. But that I'm not really sure about the licensing issues related to that, so I'm not sure. Yeah. Yes, yeah, we have multispectral cameras. We could do that. I haven't tried it out with the machine learning, for instance, but that's another attribute in the raster that can be used to train a model for sure. No, but if you can see it in the data, then we could definitely do that. Yes. Sure, yeah. We do fly power line corridors. For the machine learning, we're actually training it to classify power lines automatically for that type of scenario. We'll do volumes, environmental collections if necessary, vegetation encroachment on power lines. Yeah, we have a pretty wide range of, I focused on transportation here. That's usually where we're building an asset inventory. But as a firm, we collect for all types of clients. Yes, sir. Probably not. No, if we're gonna fly, it's gonna have to be the right conditions. So yeah, weather is definitely a factor in flight planning. Thank you.